some more time. In the meanwhile, I'd like to ask you, see, SR is one topic in physics which everyone has heard about, right? I presume everyone has heard something about SR. Science fiction movies, Interstellar, everything talks about SR, GR, all of these things, length contraction, time dilation, simultaneity. I would just like to ask you what you have heard of SR so far before we actually do SR. What do you think SR is about?
Special relativity.
Anyone? What is SR? SR is special relativity, just to clarify, and GR is general relativity. I will be using these terms. So what have you heard of it, about it until now? The faster you go, slower time progresses. Anything else? What is length contraction? What do you mean by length contraction? Even if you observe something which is not moving, it appears to be smaller than it actually is. Okay, anything else? A time dilation is what he just said, right? Okay, that is SR. What have you heard about general relativity? Like you would have heard black hole, this, black hole, that, black hole, no time, light can never enter a black hole as seen from the outside. Hawking, radiation, something you would have heard. Yes, just anyone. Tell me what you have heard about GR and black holes or whatever. Mass curves spacetime. Only mass? Even energy. Okay, mass and energy curve spacetime. What else? What does curve mean? Gravity is an effect of distortion of spacetime. So it's not a force? No. Okay. Anything else? Has anyone else heard something about GR, black holes? Gravitational waves. Have you heard of gravitational waves? What are they? Anyone has any guesses on what they are? Ripples in space-time. Okay. What exactly does a ripple mean? Like, are you saying the lengths and times get changed? Okay, fine. So more people have joined, so we will begin now.
Yeah.
Welcome to the first Guide to Galaxy session of this tenure. I am Suraj, a coordinator of Horizon. My fellow coordinator Aditya Goel is here on behalf of Horizon. Guide to Galaxy is a lecture series done by students who are members of the club Horizon, coordinators specifically. We will have many more sessions in this year, 6 in total. You guys can stay tuned. Messages will be uploaded on Astrofiles, on Aspiring Physics Guild, TechSoc, Freshie Roadmaps, etc. We also have a very special and unique first session this year because we are also collabing with the Math Club. We have the coordinators Hemanth and Sudhanvaa sitting over there, who are the Math Club coordinators. So this will be a joint session. The method will be that Maths Club will discuss the maths behind curved spaces. They will discuss linear transformations, jacobians, metrics, all of that. We will discuss the physics of special relativity and use whatever maths they have derived in our calculations. So this is a kind of unique session where mostly the maths was also done by physics people till now, and it was kind of light on the maths. This will be a very special session because the maths will also be pretty decent. So with that, I'll give it to the Maths Club to begin.
Yeah. So hello everyone, I'm Hemanth. I'm a coordinator in Math Club. So now just to keep the Enthu Josh high, how many of you participated in Integration B? Damn, nice. So stay tuned for other Math Club events as well. So let's begin with today's session. So as you all know, like this session is about the intro to special relativity, where we guys will be handling some of the prerequisite basic stuff for math. So, and our session is mostly going to be mostly intuitive. So you guys have to mostly imagine and just get the feel and flow as we go along. So let's get started. So first I'll be telling you guys what my lecture will be structured, and then we'll go on to in detail so that you will get a high level overview of what all will come next. So first I'll be speaking about what a linear transformation is and how it maps grids to grids or vectors to vectors, and then I'll be discussing about some geometric intuitive meaning of what a determinant of a matrix is, and then we'll go on to Jacobians and Jacobian determinants. So this is the high level plan of this session, and I hope you guys must have learnt about multivariable functions and gradients and all in your MA 1101 course. So it will be a build up on top of that. I think even Jacobians are introduced in that course. Is it done already? Okay, mostly it will come. So, and you will get a feel of what exactly is a Jacobian as well. So let's get started from the very basics. We'll start with the vector and end in special relativity piece. So first, you guys have heard, you can hear me right properly? Yes. So now you guys have heard about linear transformation. So let's get to there from the start. So suppose, imagine I start with some vector v and I apply some transformation, I get some output vector v prime. So what is this? This is what you call as a transformation. It takes in one vector as input and produces another vector as output. So now suppose if I tell you that, let us consider a simple case in a two-dimensional space. If I tell you that suppose this vector 0, 1, 0, if this, and suppose if I tell you this vector 0, 1, is this visible, this font size? Fine. So if I tell you that this vector gets mapped to say some vector 3, 2, and suppose if I tell you that this gets mapped to some vector minus 4, 1, suppose if I tell you this and I just tell you that it's a transformation. So can you tell where some other random vector like some 5 gets mapped to under this transformation? I've just told you that's a transformation. I've not told anything more than this. So the obvious answer would be no, because I don't know what transformation is this, and I've only told you two mappings. Like I told you 1, 0 is mapped to this, 0, 1 is mapped to this, but I have not told you anything more. So these kind of transformations are pretty useless. Like you can't do anything out of this. So what we do is we define some useful constraints which make our life simpler, and also they are good approximations. So what can we consider like that? So if I assume this transformation to be linear, so what do I mean by linear? Suppose I tell you that some vector v1 gets mapped to some vector v1 prime and v2 gets mapped to some vector v2 prime. Then if I tell you that some linear combination of this, by linear combination I mean you multiply the first vector by some scalar number v1 and the second vector by some scalar b. Then if I pass this as the input to this transformation, if I get the output to be the same scalars multiplied by the outputs v1 prime plus b v2 prime. So if this relationship holds for every a and b and every vector v1 and v2, then I call such a transformation to be linear transformation. So now if I ask you the same question now, given that this transformation is linear, can you tell where that phi gets transformed to? Yes, right. So basically I have told you that it's a linear transformation. I have also told you that the unit vectors get mapped to these. So let's see how we can tell where does phi comma phi gets mapped to. So suppose our vector is phi and I tell that I am applying this transformation to this. This is the same as applying this transformation to phi times 1, 0 plus phi times 0, 1. Can everyone see this? This is just writing a vector as sum of some other vectors. So now given that we can do this, and now since I have to assume that this transformation is linear, meaning which this is true for every scalars and every such vectors v1 and v2, I can conclude that this is the same as phi times the transformation of 1, 0 plus phi times the transformation of 0, 1. So now since I have told you where 1, 0 and 0, 1 gets transformed to, I know this where does phi comma phi gets transformed to. So basically, we can just generalize this to some arbitrary vector. Suppose this was x and this was y, then this becomes just x and this becomes y. Then similarly, this is x and this is y. So now from here, what we just do is a notational shortcut. Like we can just write this as this times this vector x, y, where I just write down the transform coordinates of 1 0 and 0 1 as this. Like for example, 1 0 got mapped to 3 2 and 0 1 got mapped to minus 4 and 1. So now this is just a notational trick to express the same thing, and I call this as a matrix. So I hope you guys would know this from, I mean, JEE time also you have done this, but this is like kind of the flow of thought. And now what is so special about this matrix? So this you can write any vector. Suppose if I give you an initial vector x1 x comma y, I can tell where it gets transformed to under this transformation by just multiplying this matrix with this vector. So now why is this useful? I mean, I said that we are defining this particular constraint. Now what is the use of defining such a constraint? Does anyone know? Anything, could be anything. Why do we study so much about linear transformations? Okay, there are multiple reasons and many factors, some of which could be like many systems that we deal in real life can be either either linear or can be approximated to be linear. So we'll see by the end of this session how this approximating transformation as linear helps a lot. So that will come along in the derivation of the Jacobian matrix. So yeah, let's stick to this linear transformation. And one more very useful property is that, suppose, I mean, I hope you guys have seen this 3 blue 1 brown ka video. So here, suppose, wait, why is this not playing? So now one more thing in this linear transform is that origin gets mapped to origin itself. So now wait, I think I should have put loop. So now suppose this vector 0 1 got mapped to some vector here, and 1 0 got mapped to this, and 0 1 also gets mapped to something else. So as you can see from this visual, every other vector is also getting mapped to some other vector, but this transformation is in such a way that this grid, you can think of it like a grid is getting mapped to another grid. Instead of just one vector to another vector, you can think of it like a grid to grid mapping as well. And one useful thing about this grid to grid mapping is that you can see that if I consider some patch in the original grid having some area A, then the same patch after transformation, the area of that will be some constant times that area A. So you can prove that this constant is same for every patch. Like if I consider some different patch over here and I see what will this get mapped to after transformation, the ratio of the areas will still remain the same constant C. And does anyone know what this constant C is? Yes. So basically this constant of by which the areas get scaled is the determinant of this matrix. So in fact, like I'll just tell you one thing, like in there's a linear algebra course by Gilbert Strank sir. If you see that, like I guess most of you in your JEE time when you first saw a determinant, you would have been introduced it as some formula, like for a 3x3 matrix, this is the formula for a determinant. You can derive that formula and even for an n cross n matrix using just this visual proof. Like you can prove some properties from this visual intuition, and if he just defines some 3 properties as the definition of a determinant, and from that you can derive every other property, and hence determinant is not some abstract thing which just came out from some random place. You can derive it just from this intuition. You can try that after this session if you want, and yeah, mostly you'll see his playlist next semester, I mean if you have the course. I mean, fine. So now coming back to our main point. So what was the main key takeaway from this discussion is that determinant is the scaling factor by which areas gets transformed to. So now let's move on with something known as what is known as Jacobian, and to motivate that I'll take an example and illustrate why did we even come up with that. So oh, Achintya, shall I erase this? Fine, let it be. Okay, so now is everything clear up until this point? Fine. So now consider that, first I will give you some physical example to motivate this. Consider that you have some disk of mass m and then surface mass density some sigma, and you want to, it's a uniform disk, you want to calculate its moment of inertia about this diametric axis. So you guys would have solved this during JEE as well. So like basically the moment of inertia formula is integral dm times r square, where r is the distance from this axis. So if suppose this is some small dm mass element, then you consider the perpendicular distance from this axis and integrate this over the entire mass. So you basically do this to find the moment of inertia. So where is this one? Fine. Is this visible properly? Like I am writing on the same thing, so fine. So now suppose you start off with some coordinate system x and y, and you try to evaluate this integral. So what will happen? So now consider that for some given x value, I consider this particular strip because it has the same distance from this axis. So I have this small dm mass. I'll do this a little bit fast because mostly you guys would know this. So now just tell me if you can understand this. This is the same as the integral of, since there are two variables x and y, I have a double integral here instead of just single one over there. So what will this value be? It is dm is that mass density at that point times the area element of that. So for now I will assume that the area element is dx dy. We will get back to this. This is the key main point of why we are discussing all this. So for now let assume that this area, small area element is dx times dy. This is the mass dm times r square. So what is the distance of this from the axis? It is just x square, and this I have to integrate for a given value of x. Y goes from here, y goes from here till here, and such strips x goes from minus, suppose that the radius is some r, so x goes from minus r to plus r, and where does y go from? So you can create this right triangle here. This is r, this is x, so this would be root of r square minus x square. So y goes from minus root r square minus x square to plus root r square minus x square. So this is the moment of inertia of this disk. So is this point clear? Like do you guys get a feel of why, how did this come? This is basically substitution here, and main thing is, are you clear with these limits? How did we get this? So we considered some strip and then integrated it from, like for a given x, y goes from here to here, and such strips goes from minus r to plus r. So this, as you can see here, evaluating this is a bit complicated, like and partly the reason is because the limits are not constants. This limit is constant, but this limit is a variable. Here the limits are going from, you can rewrite this as some like sigma times dy dx, where first y goes from here to here, then x goes from r to r. So the reason why this becomes a mess is because the limits are not constant. You can evaluate this in practice, like you can try that and you will get the correct answer as well, but it's difficult to work with. So we want to make our life simpler. So what do? Suppose here first we started off this problem by saying that I'll assume my coordinate system to be some x axis like this and y axis like this. So this is where we started. So suppose instead of starting that way, suppose what if we start something like this? I'll define my coordinate system. Have you guys heard of polar coordinates? Yeah, right. So if this is at some distance r and some angle theta, so this polar coordinate r comma theta, I can say that the corresponding point is some x comma y, where r cos theta is x. This is all basic stuff only, so I'll go a bit fast. R sin theta is the y coordinate. So if I try to evaluate this same integral in polar coordinates, what will that be? So that will basically be, again I have two integrals because I have r and theta. Then what will that dm mass element be? That will be this mass density times the area element. So now what do you consider as area element here? Yes. So it is just r dr d theta times the distance of this point from the axis, which is basically r cos theta. And what are the limits? Here for every particular theta, my r goes from 0 to capital R, and for every particular r, my theta goes from 0 to 2 pi. So basically I can express this as first r goes from 0 to capital R and theta goes from 0 to 2 pi. So as you can see, this is a much simpler to work with because we have constant limits and hence it is simpler to evaluate as well. So why did I discuss all this which you guys mostly know? I mean, you guys answered this area element as this. So the main thing is, how did you get this r here? Why is it not simply dr d theta? Yeah. Oh yeah, r square. Sorry, my bad. So you have r cos theta, that distance ka whole square. So now the key thing is, how did you get this scale r here? Yeah. Yeah, so basically we are heading towards Jacobian. So you can find this scaling factor by knowing what is known as a Jacobian of a determinant which I will construct in few minutes. So now basically can we somehow take inspiration from that? There also we had some area element getting scaled by some factor. Here also we have some area element getting scaled by some factor. So suppose instead of this, the same thing, let us make this much more complicated by considering, suppose you have some n dimensional vector x1 to xn, and suppose this is one coordinate system. In this 2-dimensional case I had just area elements, in 3-dimensional we will have volume elements, and in this some hypervolume will be there. So now suppose I am working with this system and I want to convert it into some other system y1 up to yn, and suppose for some reason this it is easier to work with this system. So now how do I convert this? This function, evaluating this, getting this function is simpler because we know this. I mean this part here we know this relation, so we can evaluate, substitute like x square, x was this, so I substituted that and I got this. But how do I get these area elements or volume elements from this? So that is basically where our Jacobian determinant comes into picture. So in order to logically proceed from here, so let us first, I will make an assumption that all these yi's y1 to yn are now, as you can see here, how did I get this y1 to yn? Suppose I assume that this y1 is some function f1 of x1 x2 up to xn, y2 is some another function of x1 x2 up to xn, and so on. Yn is some fnth function of x1 to xn. Suppose this is the particular transformation that I am speaking about. So now here this is what we will eventually land up, but now suppose I want to proceed from here. So let me make a simpler assumption. Let us assume that all these functions f1 to fn are linear functions of these inputs. So if I assume that they are linear functions, that will make our life simpler, and I will also tell you how we can generalize this to some non-linear arbitrary function as well after this. So now what am I telling? I am telling you that assume that this y1 up to yn is some constant a11 x1 plus a12 x2 up to a1n xn and so on. So this is an1 x1 plus an2 x2 up to ann xn. So like you can write out every row here. So if I assume that this is the particular function that I am working with, this is the transformation that I am working with, in that particular case you can express this from our earlier matrix ka notation as this whole matrix a11 a12 a1n up to an1 and so on times x1 up to xn. So this is my new coordinate system y1 up to yn. Is everyone clear till here? So what did I do? I first started with a 2-dimensional case, took an example, then we generalized it to an n-dimensional case, and then after that in this n-dimensional case the mapping that I am speaking about, we first restricted it to just a linear map, and now we will try to derive some things from here, and after that we will again generalize back to non-linear functions. So this is how it will be structured. So now for this, what can I do with this? As you can see from this, and as I explained in the start, these linear transformations are good transformations, meaning the area elements, volume elements, they get scaled by a factor which is a known thing, which is the determinant as you saw here. So now when I map every point in this x1 x10 coordinate to some point y1 yn coordinate, then it's like that grid transformation or thing that you saw here, right? It's the same thing in n dimension as well. So now you can, it is very easy to visualize that in this n dimensional space, if I have some volume element here dv, note that I didn't write like this is some dx1 dx2 so on, because this need not be Cartesian always. So suppose this is some volume element or some hypervolume thing dv. Now how is it related to this dv prime here in this coordinate system? That is basically the determinant of this matrix times you just have to multiply it with the determinant of this matrix. So now this is some special matrix like which is giving me the scaling factors. So we call this as a Jacobian matrix, and the determinant of that is the scaling factor. So till now it is fine, like we were able to solve for any linear system what will be the scalar multiple, and we can also find out like such volume elements, area elements, and convert basically the analysis that you are trying to do in one coordinate system, you can easily convert it to another coordinate system given that there is a linear mapping between them, because you know this. So now it will not be the case that every time you have a linear transformation, right? So we want to go from linear to non-linear functions. So for that a very useful approximation comes into hand. So what is that? You guys have seen this some picture, right? So you have some one dimensional function, and around any point what I can say is this function can be approximated by a straight line. Like if you zoom in very much, it is approximately a straight line. So that is why we define what is known as the derivative, and then we say that around this point we can assume that y is equal to some slope times x plus c. So this is around this point x comma y, not somewhere else. So since around a point in the close neighborhood I can assume that the function to be a linear function, we'll do the same trick here as well. So in this n dimensional space also, around any point, suppose I have some point say x1 x2 up to xn, around this point I consider some small vicinity around this, then I check what will be the what will this get mapped to some other small area or volume element here. This same point, the points are the same but they are expressed in different coordinates or languages, so y1 up to yn. So now if I know that what is the scaling factor for this, suppose it is some number 2. Now suppose if this scaling factor is known, but the good thing about linear transformations was that the scaling factor was constant for every point in this space. But now for a non-linear function, this point, the close neighbourhood has scaling factor 2, but some other point might have a scaling factor different. So the scaling factor depends on at which point you are. So what we can do is around this point I can say that y1 is some number times x1 up to some constant times xn only near in the close neighborhood here. You can see that I didn't put a constant c plus c here because it doesn't matter, because what we are mostly interested in is the change in x and change in y's, so that constant just goes off. So this number over here is basically the partial derivative of y1 with respect to x1. I hope you guys would be familiar with this partial derivative from MA 1101. If not, it is basically just keeping all the other inputs constant, you differentiate, vary only one and differentiate the function, and so on. Like this will be del y1 by del xn. So this is the partial derivatives. You can express this function, that mapping f1, this is basically f1 of all those inputs. Similarly, I can represent all these f1 to fn as this partial derivatives times the inputs, and I can since I am able to do this, I can also write this in a matrix form simply as y1 up to yn is del f1 by del x1 up to del f1 by del xn and so on. This is del f n by del x1 up to del f n by del xn times x1 up to xn. I hope this point is clear now. Like it is basically the same thing. I didn't write out any equations here. Each of these are the partial derivatives, And how do we get this? Because I assume that around that point it's a linear map. So in one dimension it's like the straight line, in two dimension if you have a two-dimensional function it's like a plane around that point, and so on. So now since I have assumed this to be true in the closed neighborhood, I can say that a small area element or volume element around this point gets transformed by a scaling factor which is equal to the determinant of this matrix. So hence we call this useful matrix as Jacobian matrix. And since one more thing that you can note here is each of these partial derivatives are a function of these inputs itself. So and since these are not just constant numbers, I get different values of this determinant for different points. So what does that mean? Suppose I have a point here, around this point the scaling factor may be 2 and around some other point the scaling factor may be 5. So if we know that the scaling factor around x comma y is something, then what I can basically do is, so here what we were doing is around some point, okay, let's come back to this later on. In that earlier Cartesian wala example is much simpler to tell. So suppose I have this, so what we said is the area element is some around this is some dx dy. Now if after I do some linear transformation I get irrespective of what this point is, the new coordinate system, the area element dA in that will always be the same constant times this original thing. I had that constant everywhere, but now since it's a nonlinear transformation, I don't have a constant scaling factor. I have that scaling factor varying with every point. So that is basically the determinant of the Jacobian matrix which tells me every point. So now from this what we can do is if we have some n-dimensional system which we want to analyze, you have some integral of this sort. So you know that the functional value at every point can be transformed using these equations, and you know also how to transform area elements and volume elements. So since you know that, you can analyze any particular system in any coordinates. So this is just an intro to what a Jacobian matrix is. There is another interpretation of Jacobian matrix which is basically it's a high dimensional derivative which you will mostly explore in your MA 1101 course. So giving this basic intro, now I will hand over to my friend Sudhanvaa. He'll yeah. Oh yeah, you are asking how did I get this matrix? So basically I didn't write it out here, I just told it. So what I did was the first function here, like I told that this function can be expressed as some scalar times this plus this times this. No? So I told that this is del f1 by del x1 times x1 plus some del f1 by del x2 up to del f1 by del xn times this x1 to xn, and same way I do the same approximation for all these n functions, meaning I write f2 also as del f2 by del x1 del f2 by del and so on. So basically like if you write them as equations this way, you can again write them in the matrix notation. So I hope that is clear. Yeah. Yeah. No, like how are we transforming this? I know these functions, right? f1 to fn. So given that I know this, I can transform any x1 to xn to y1 to yn. So what are these functional equations? In this example, these are my functional equations. Meaning, suppose if I tell you some point, say r theta, I want to convert this to some point xy. How do I do that? So x is so basically your xy is r cos theta, r sin theta. So these are the functions basically that I was referring to till now. So from this, so you can basically derive like you can write xy is r cos theta, r sin theta. From this you take partial derivative of this with respect to x, partial derivative of this with respect to y. It is just a 1 minute calculation I will do off. You get some r and theta. So if you differentiate this partially with respect to r, you get cos theta. Then differentiate this partially with respect to theta. Matyam, Sriyat. just one second. I mean, I thought he'll cover this, but fine. Partially with respect to theta, you will get minus r sine theta. Okay, wait. I'll write this here. So basically, we had this xy is r cos theta, r sine theta, right? So now from this, I can also write this as around some neighborhood. This Jacobian matrix can be constructed as partially differentiated this with respect to r, you get cos theta. With respect to theta, you get minus r sine theta. Then with respect to again r, I get sine theta. Then with respect to theta, I get r cos theta. And when you take the determinant of this, you get cos theta and cos square. So it basically becomes r cos square theta plus sine square theta, which is basically 1. So you get this Jacobian of this determinant, determinant of this Jacobian as r. So this is how you get these scaling factors. So you can do this, you can even try it out for spherical coordinates or cylindrical coordinates. If you just know this conversion formulas, you can derive Jacobians for all. Yeah. Because it's an approximation, it's not an exact value, and it's since what you're doing is at every point when you're calculating this volume element, I'm only telling when I started off I said that this is some dm mass times this distance. You can assume this distance is the function at this point times this small sigma times that distance as, if you assume that as my function f. So what I'm telling is that the small dA element that I'm considering here, since it is very small, I can assume that it's a linear, the function to be linear, and hence I can express the same thing in polar as well. So it's just an approximation that we are doing, and since we are doing this, when we are integrating, we add up all point masses or point by point, right? So that is why we can say that this approximation holds. So was that clear?
So by the time the board gets cleaned, I'll just ask you guys a few questions. I want you guys to interact on this, okay? So 2 points here, okay? So these are the coordinates. What do you mean by the distance between these 2 points? I want someone to answer. What is the distance between these 2 points?
Which you want to use this board, right?
I'll use both.
Okay.
Correct? None of you know this. Okay. Okay, why is the distance defined like this? Why? So what is this actually? It is the length of this path, right? Why should I not define the distance like this? Can you all see this, what I have written? Huh? Why is Pythagoras correct? No, wait. So, but even this makes sense, no? You're saying how far away you're in this direction and how far away are you in this direction. Correct. So, what is the basis by which you're saying Pythagoras theorem is correct? So there should be something more fundamental about the notion of distance. Are you able to understand what I'm telling you? There is something more fundamental in this. So what I'm trying to say is, we'll first define what D should be, okay? This is going to be a little abstract, but just try to hold on, okay? So now I will say I have a set X, okay? So this can be the set of all vectors, okay? Whatever dimensional space I'm in or whatever objects I have, I put all of those objects in one thing called a set. I call that set X. Now I define a function D which takes 2 vectors in X or 2 objects in X and maps it to a real number. Fine. So that is what a distance is, a real number, no? Now this distance function should have 3 properties. Okay. we'll just define all those three properties from the intuition of distance we have. We have not defined distance the Euclidean way. The Euclidean way is using Pythagoras theorem. Okay. The other one where I wrote using just the sum of two absolute values, that's called, doesn't even know. It's called the Manhattan distance. Okay. There is nothing wrong about that as well. Even the Pythagorean theorem is correct. They are just two different ways of telling distance. Fine. So, both the distances we defined before this, one is the Pythagorean theorem, that is called the Euclidean distance, and the Manhattan distance, they follow these three properties. So, just by intuition we will write these three properties. Okay. One, this takes two arguments. Okay. So, one is, let me just call x comma y, they belong to the set X. So, now this has to be greater than 0. Does that make sense? What do you think it implies about? So, if distance between 2 points is 0, it means the 2 points are the same point. Does this also make sense? And the third one is something called the triangular inequality. So, the shortest, if you take a detour from your shortest path between 2 points, you are always going to increase the distance. So, any function d which satisfies these three properties can be a proper or a valid distance function on the set X. Okay, X can be R2, X can be R3, or X can be anything. Works? So, you take a pair, you take the set X and you define the function. This is called a metric space. So, whenever you work with something in relativity, you should first define your metric. Okay. So, you should say I am working in this space and I am having this as my distance function. Clear? Amazing. Next is, okay, now that we have understood a very general notion of the distance function, we will move on to something called the line element. So, how many of you have mechanics 1 or physics 1? Most of you. So, you would know something called line element, no? So, what do you write line element ds square in Cartesian coordinates? Very good. So, does this look like the Pythagorean theorem? Now, what is this in polar coordinates? Does anyone know? Let's draw it out. I want you guys to tell me the answer. Okay. So, this is my x axis, this is my y axis, this is my z axis. Okay. Now, I have a sphere and I have a vector here. This distance is r, this is theta, and I project this is phi. Okay. So, if I want the distance from here to this part, what do I actually want? I want the distance in 3 perpendicular directions. Correct. So, now I am here. So, first I have r, so I will move dr in this direction. Okay. Now, if this is r, what is this radius here? R sin theta. Correct. And you see theta here. Okay, I will draw this in here. If this is theta and this is r, what is this length? R theta. Correct. So, if this is d theta, this is going to be d theta. And as theta is very small, this is almost equal to the straight line distance. So, here, if I increase theta by a little bit, it will become r d theta in this direction. And r sin theta is like this. So, if I move in the phi direction a little bit into the board, the perpendicular direction would be r sin theta d phi. Correct. So, now what would be the line element? It will just be the squares of those three numbers added. Correct. So, Is it clear at least until now? I want a yes or no. Clear until now. So, what I want to tell you from this is, just by taking the squares of these vectors. So, whenever you work in physics, you say there is a coordinate system, okay? And the laws of physics are always invariant under any coordinate transform. It should not, the physics should not change. Whether I am seeing everything or someone else there is seeing, or you are moving and seeing the system, whatever you observe should be the same. So, coordinates should not affect the physics of the problem. So, now first, I am in 3D space. So, I have 2 points. It should not matter if I am looking at these points in terms of x, y and z or r, theta and phi. Okay. So, now when I am saying the distance between 2 very close points is just square these small distances and add them. But here when I am squaring and adding the distances, I see there is some extra terms here. You are getting my point now? In normal xyz coordinates, these coefficients were just 1, 1 and 1. But when I change my coordinates, it is becoming 1 r square and sine square theta. So basically what I am trying to say is, when you work with different coordinate systems, the distance between 2 points would keep changing. It would just still be, I will get rid of these things, so I get some more space. You are done with this? So now if I am working in a coordinate system where I have x1, x2 until xn, the distance between 2 points would be dx1 square plus dx2 square until dxn square. Then there is also a possibility that you can have terms like dx1, dx2 and so on. So you will have all those many combinations. Okay, so what the thing is, this is not complete. There are always some terms here. Okay, so you saw it was r square and r square sin theta in the previous case. So there are some terms here. Okay, so now what would these terms are something called Gij. Okay, so basically what you write is, you write ds square as summation over all I and j, Gij dxi dxj. So can you guys see that G is a matrix here? I can go from 1 to n, G also can go from 1 to n. So if you are working in the normal xyz coordinates in n dimensions, so you have x1 until xn, this matrix would actually be an identity matrix. So that is why in the normal space you write d square as dx1 square plus dx2 square until dxn square. So this idea of having coefficients here is way more general. Understood? So what this enables us to do is, in relativity, you actually write time as the 4th dimension, right? So you say I have c square dt square as my 4th dimension, and then you take dx square plus dy square dz square. Now you negate this term and add them. So time is being the dt square of 4th dimension, but time has c square as its metric. Okay, after, I won't take too long, I will take 5 more minutes. After that you will see horizon, you will see the physics of relativity, then they will actually derive this and you will get a better feel of this. Yeah. Yeah, fine. That is simple. We will just do it for the R3 case. This is correct. So now if I put I equal to j, I would have Gii dxi square. So when I have G1 here, I have G11. So G11 is dx square. So the coefficient is 1. But this does not have dx dy terms, no. So whenever I is not equal to j, the elements are 0, and whenever the elements are same, so I have dx dx or dy dy or dz dz, I see the coefficients are 1 1 1. So this is the metric Clear? No. This is only for metric for Rn. So the normal rectangular coordinates we work with, that is the metric for that. It will be different. That's what I am telling you here, no? So when you work in relativity, special relativity, you have c square dt square term. So this would be actually one of the elements in the diagonal. The others would be -1. So now we saw that yes d y I. So this Hemanth derived this, no? He said the Jacobian matrix has these as its elements. Correct. So now what happens is, now if I know the metric in rectangular coordinates, so I am in one coordinates, I see the problem is easier if it is solved in some other system. Okay. So when I change my coordinates, you know that even line elements are changing, because the line element in normal 3D coordinates is not the same as when you work with polar coordinates. So how the metric changes? This is how the metric changes. Okay. So you have the Jacobians involved there. This part I will not be deriving, but I will just give you an intuition. Okay. So now you look at this. Here you are seeing a very nice transformation where parallel lines are getting mapped to parallel lines. Okay. But what happens in a manifold? A manifold is any space where you go very close to some point. What you see is it represents a linear transformation like this. So you can have the initial space can be rectangle like this or squares like this, but finally it can become something like this. Okay. So there is some very non-linear transformation which takes space like this and makes it to something like this. But what happens is you go very close to this point, it will still look like this. So what we do is we only work with these. This transformation is what is being taken care by the Jacobian. You see, for this case, if you remember the first matrix we derived, it had only constant numbers. I think he took it as 4, -1, 3 and 2. So there were nice numbers there. But now you are seeing all weird partial derivatives coming up. Why is it? In the vicinity of any point, the transformations will look linear. That is what it is saying. Okay. So due to time constraints, I'll stop here. I think we know some good amount of math to start with relativity now. Thank you.
Alright, so finally we are done with the maths part and we will begin the physics part now. So we are going to discuss special relativity today. So first of all, what is a relativity principle? Can anyone tell me what is a relativity principle? What does it tell you about? Anyone, guys? Come on. Okay, fine. So a relativity principle, So a relativity principle is a statement of what the invariant properties of a system are. So what are the invariant properties of a system? Those are the properties that do not change even if we look at them from another frame of reference. So any examples for such properties of a system that do not change even if I change my frame of reference? That remain the same in all inertial frames of reference. Louder, louder. Fine. So rest mass, rest length, it will remain the same in all frames of reference. Pay attention to the word rest. Alright. So coming to the first relativity principle that we will discuss. So that is Galilean relativity. So Galilean relativity principle tells us that It's the laws of motion that remain the same in all frames of reference. So F is equals to ma remains F is equals to ma, like it won't change. Laws of conservation of energy will remain the same in two frames, inertial frames of reference. So Galilean relativity principle tells that the laws of motion are the same in all reference frames, and it also tells us that all motion is relative to something else. There is no concept of absolute motion or absolute state of rest. So you guys might say that I am at rest with respect to you, but however a person in space on space station will say that I am moving at a speed at which the earth rotates with respect to him. So there is again no concept of absolute motion or absolute rest. Everything is relative. That's what Galilean relativity principle tells us. I'll give you an example. So suppose this man is standing by a road and the car passes by moving with a velocity v. So we are talking about inertial frames of reference, just to be clear. Yes. So to explain reference frame to you, so if I am observing you, I am observing you from my reference frame. If you are seeing me and looking at me from your reference frame. So if I move in my reference frame, I am still. However, in your reference frame, I am moving with some speed or acceleration, whatever. So reference frame is like seeing things from different points of views. You can call it coordinates, fine. So there are two reference frames here. One is the man's reference frame and one is the driver's reference frame. So this car is moving at a speed v with respect to the man. So the man will say that the car is moving at a speed v with respect to me in the forward direction. However, the person sitting in the car would say that the man is moving towards the left with the speed v as per him. So Galilean relativity principle says that both of them are correct in their own place. There is nothing wrong any of them is saying. Both of the statements are equivalent and there is nothing wrong in saying either of them. So this is a more formal definition by what I mean by no absolute frame of reference. No mechanics experiment carried out in one frame of reference can tell the observer in this frame what is the motion of this frame with respect to any other inertial frame of reference. And there is no way of determining the absolute velocity of the inertial reference frame, because to determine the absolute velocity of an inertial reference frame, I need an absolute frame of reference, but that does not exist according to Galilean relativity principle. So since we are doing a change of frames of reference, I need a transformation to find the space-time coordinates of an event. So event is a point in a space-time diagram, and so since we are comparing an event in two reference frames, a Galilean transformation gives me the formulas to write the same event in both the reference frames. So one key thing about Galilean transformation is that you can see that even if I change reference frames, the time coordinate of the event remains the same. That is, two observers in inertial frames of reference will not disagree upon their notion of time according to Galilean transformation and Galilean relativity. All inertial reference will agree upon time. However, turns out Galilean relativity principle is not complete and has some faults. It fails at relativistic speeds, that is speeds closer to speed of light, and experimental data differ from data predicted from theory. So we'll one by one look at some of the problems. So there is an example. So there is an electron with an energy of 10 mega electronic volt, and we are increasing its energy to 40 mega electronic volts. So if you do the kinetic energy equals potential energy calculations, you would say that the velocity of the electron should double from 0.9988 c to 1.9976 c. However, experimental observations tell us that the speed of the electron does not exceed the speed of light. So that means there is some problems with the Newton's formulation as well as Galilean formulation. The second dilemma we have is Galilean relativity principle only talks about laws of motion. It does not take into consideration other laws of physics. So I don't know if you are familiar with Maxwell's equations or not. So basically del dot E is equals to rho by epsilon naught is just another way of writing the Gauss's law. So Gauss's law is written as E dot dA is equals to Q by epsilon naught. So you study the properties and there is this divergence theorem which says that this thing is equals to del dot E d tau integral is equals to Q by epsilon naught. So you can write Q as rho d tau, you can put an integral, and then you can say del dot E is equals to rho by epsilon naught. So this del operator is called the divergence of the system. and you can formally write it in Cartesian coordinates as del by del x I cap plus del by del y j cap plus del y del z k cap. So these are the Maxwell's equations which govern the electrodynamics, and we see that upon solving these equations to find the wave equation of light, there is an inherent constant in them. You must have derived them in your school days as well, that speed of light turns out to be 1 by root mu naught epsilon naught. So while doing this derivation, we have nowhere taken into consideration any frame of reference. Maxwell's equations do not talk about any frame of reference whatsoever. So the question comes is, what is the speed with respect to? In what frame of reference is the speed of light c? And what about Galilean relativity? Because Galilean relativity principle tells us that all motion is relative to something else. So what is the speed with respect to? And if this is with respect to some frame only, then our laws of electrodynamics valid in only that frame. So there is all kind of confusion that is coming in here when we consider Galilean relativity principle and electrodynamics. So we can see that Galilean relativity principles preserve Newton's laws, but however they fail to preserve Maxwell's equations. However, if we want both of them to be correct theories, there should be a specific frame of reference in which the speed of propagation of electromagnetic waves is c as given by Maxwell's equations, and there should be some medium relative to which the speed of light is as obtained, because again the Galilean principle talks that all motion is relative to something else, so there should be a medium with respect to which the speed of light is c. So there are three probabilities that are in front of us, that a relativity principle exists for mechanics but not for electrodynamics, and there is indeed a preferred frame of reference for electrodynamics in which the speed of light is c. The second probability that we have in front of us is that a relativity principle exists both for mechanics and for electrodynamics. However, the electrodynamic equations given by Maxwell are incorrect. Third probability is that a relativity principle again exists for both mechanics and for electrodynamics, but there is some problem with Newton's laws and Galilean transforms, and Galilean relativity principle is somewhat incomplete. So we will one by one explore all these probabilities. So to explore the first probability, that is to find a medium with respect to the speed of light is c, we did this Michelson-Morley experiment. So the apparatus, as you can see, there is a light source and there are two mirrors and then there is a screen. So it is, and there is a partially reflective mirror. So partially reflective mirror reflects some part of light and refracts some part of light, transmits some part of light. So it is based on the concept of path difference. So if the speed of light in directions A and in direction B would be different, we would see the interference pattern changing as we change the speed of lights in both the directions. So if there is suppose a frame of reference that we call an ether frame of reference, that is in the plane of the sun. So earth is moving through that ether frame of reference. In that case, there should be some ether winds, that is for a source of light that is on earth, the speed of light should be some c plus v. So in different directions, the speed of light should be different depending on in what direction the earth is moving through that ether frame of reference. That means throughout the year in different seasons, we should observe the change in interference patterns continuously. So these two guys carried out this experiment for about 1 year or many years, and they found out that there is no change of interference patterns obtained on the screen. So this was a huge breakthrough, as it led to the discarding of ether hypothesis. There is no special frame of reference. Second probability, that laws of electrodynamics are correct. So to completely discard a theory, we need experimental evidences and experimental deviations. Laws of electrodynamics have not shown any deviation experimentally. However, we have seen that Newtonian mechanics and Galilean relativity principle is somewhat faltering. Hence, sorry. There is some problem with the keyboard. Yep. So no ether and Maxwell's equations are also not incorrect. So that means our third probability is the correct one, that there is some problem with the Newton's laws and Galilean relativity principles. So this brings us to our special relativity principle, which is an extrapolation of Galilean relativity principle to make it more complete. So Einstein said that instead of just laws of motion, all laws of physics in their completeness are the same in all inertial reference frames, and he also included that the speed of light is also same in inertial reference frames. Now he termed speed of light as a law of physics and termed it as an absolute constant. So there is now no confusion that in what frame of reference is this and what is this with respect to, because he totally said that speed of light is absolute and it does not change in different frames of reference. So what does that mean for us? We need now a new transformation of coordinates. Why? Because the Galilean coordinate transformation was something that like x dash is equals to x minus vt. So if I differentiate, so v dash is equals to v minus, sorry, what did I do? Sorry, u minus v, where u is the speed in the x frame of reference and v dash is the frame in the x dash frame of reference. So that means if I see light from in a frame of reference that is moving with a speed v with respect to that frame of reference, the speed of light should change. That means Galilean transformations do not conserve the speed of light. Hence we need a new transformation of coordinates, and that is our Lorentz transformation. Yes. Yes. So we'll discuss about it as we move throughout the session. So this special relativity principle is more or less concerned with non-accelerating frame of reference. We think about accelerating frame of reference and gravity and all in GR. SR only comments about non-accelerating frames of reference. Fine. So now again we'll discuss the key aspects of this Lorentz transformation. It is that time is no longer absolute. So two observers in two different inertial frames of reference will no longer agree on the notion of time as well. Time is no longer absolute. So when we talk about a transformation, so it transforms both the coordinates as well as the basis vectors. So in Galilean transformation there is no change of basis vectors. However, in Lorentz transformation there is a change of basis vector, and this change of coordinates and basis vectors is in the opposite ways, and we call this as covariance and contravariance. Moving forward, so to sum up, what we are doing is Maxwell's equations force C to be invariant, and the only transformations that are leaving those equations unchanged are the Lorentz transformation. And these transformations are preserving the space-time interval just like rotations preserve distances. So Sudhanvaa told that there are, if we have a space-time, if we have a vector and we rotate it by some amount, the length of the vector remains same. So distance remains the same if we rotate. So these transformations are just like rotations in the Euclidean geometry. Now since I mentioned space-time interval, so what is a space-time interval? So this is my space-time diagram. So you must be thinking why x is on the x-axis and time is on the vertical axis. So this is a general convention that we have used in relativity, because we are particularly interested in the leftward or rightward motion of an object, and we are particularly not interested into like go back in time or something. So it is a more convenient representation. So any point in this space-time diagram is an event, and the vector between these two events is called the space-time vector, and the distance is called the space-time interval. So this distance is given by c square t square minus x square minus y square minus z square. So why is this negative sign coming in? Position coordinate. So it's you cannot draw 4 dimensions, so we are working with just the x coordinate and the time. I can draw a y axis for you, but I cannot draw the z axis for you, unfortunately. So yeah, so I was assuming you might ask question, where does this negative sign come from? Any ideas? Time axis has? That is actually not a correct way to represent it. Many books use it, but that is not the correct way to represent it. So the thing is, it all boils down to the same thing, that we wanted Maxwell's equations to be invariant. Now to do that, this imposes another constraint on what kind of metric we choose. So the only metric which preserves Maxwell's equations and preserves our space-time interval as well is this diagonal matrix, that is -1, 1, 1 and 1. Or we can change the sign, +1, -1, c square. So it is again a convention if you want to do minus for time axis or positive negative for that. So this was about a space-time interval. The maths of it is pretty complex. If any of you is interested in it, you can maybe come after this session. So this is a space-time vector, and as I defined, the event is something that happens independently of the reference frame we are using. So event is another invariant that we have defined, because so a collision of balls will remain a collision of balls even if we change our reference of frames. The velocity of the balls before and after collision might change, but collision remains collision. So event is something like that happens independently of the reference frame, and the space-time coordinates can vary based on different reference frame. So an example for this, suppose I want to mark the tip of the pencil using my, so I have two orthonormal bases here, one is the blue one and one is the red one. So, so I want to mark the tip of the pencil. So the person in the blue reference frame says, blue coordinate system says that the component, x component of the pencil is 4 and the y component of the pencil tip is 3. However, the person who is using the red orthonormal basis will say that the tip of the pencil is at 5 in x coordinates and 0 at y coordinates. So again, tip of the pencil remains the tip of the pencil, however the coordinates are varying depending on what basis are we using. So I talked about how space-time remains invariant. So Lorentz transformation is again very special in the sense that they keep our space-time interval invariant. So the person in the x tilde, so this sign is called tilde. So person in the x tilde frame of reference would say that the space-time interval is ct tilde square minus x tilde square. So both these observers, even after do a Lorentz transformation, will not disagree on the space-time interval. And you can see the maths behind it. I am not going to cover it because we are short on time. So ct tilde square minus x tilde square remains ct square minus x square, and space-time is invariant in that sense. Okay, now coming up to a very interesting part of it, time dilation. So what do you guys know about time dilation? Come on guys, I want you to be interactive. Faster you move, the slower you age. Okay, anyone else? Yes. So Maxwell's equations need to remain invariant. We discussed that there is no fault with Maxwell's frame of reference and they do not talk about any reference frame whatsoever. That means they are invariant, and see, special relativity principle told that all laws of physics remain the same in all reference frames. That means all laws of motion including laws of electrodynamics should remain the same in all frames of reference. That means coordinates will change again, the law will remain same. So you might argue that suppose in a collision that is happening in one frame of reference, so suppose energy is getting conserved in one frame of reference, energy will remain conserved in even another frame of reference. However, the velocity, the way you write kinetic energy, the way you write potential energy will change based on our reference frames. The principle of conservation of energy will remain same in all the frames of reference. So again, your definition of del might be gradient and all might change depending on a reference frame. However, that del dot E equals rho by epsilon naught, this will not change. That is what I mean when I say laws of electrodynamics are invariant. So time dilation, time dilation. So someone at the start of the session says the faster you move, the slower the time goes. So that is partially correct because your clock would keep moving at the same space with respect to yourself. The correct statement would be the faster you move, the slower your time appears to move to another observer at rest with respect to you. That is the correct definition of time dilation. And now I'll discuss why does this happen in the first place. What is this? So suppose I have a person who is standing still and his coordinate system is x, x and t. So he is at origin and he decides to clap his hands at an interval of 3 seconds for some reason. Now another person who is moving at some speed close to c. So according to the Lorentz transformation, his coordinates would be something like this. Basically his orthonormal basis will also get transformed and his transformation look like this. Now this time interval, so first of all, what do we mean when we say we want to measure a time interval between two events? Is it the difference between the time coordinates or what? this is not the difference between the time coordinates. The measurement of time interval is clearly stated that time measurements should be made along lines of simul position. What do I mean by lines of simul position? So what do I mean by lines of simul position? That the position of the object should remain same when I am doing the time measurements between the two events. So you can see in the observer O's frame of reference, the x coordinate is not changing, and hence he is taking the time interval delta t is equals to 3 seconds. However, if I want to measure the same time interval in this guy's frame of reference, so if I project it here, so you can see that these 2 points in this guy's frame of reference are no longer at the same x coordinate. So we are violating the definition of how we measure time interval, and we are rather focusing on the difference in the time coordinates instead of focusing on delta t, how it's defined. So this guy, this length as you can see is of course longer than this length, and he would say that these 2 claps A and B happen at t greater than 3 seconds because this length is longer. So the main point being that whenever you are making a time interval measurement between 2 events, you should be at with respect to the events. If you are moving with respect to the events, this kind of confusion arises, and hence we might say something like moving clocks run slow. Moving forward, so moving clocks run slow means that a clock moving at a constant velocity relative to an inertial frame containing synchronized clock will be found to run slow when timed by those clocks. So it is all relative. There is nothing like the clock needle is slowing down or something is happening. Just the person in another frame of reference will see his time measurements to be different than the other person's time of reference, because he is measuring the difference in time coordinates rather than measuring the proper time as it is defined. Now length contraction, is that also yes, so lines of simul position are the lines along which the x coordinate remains the same. So if this is my space-time diagram, these are my lines of simul position. So this is my line of simul position. So time goes on, but the x coordinate remains the same. So as for this thing, to measure this time interval, the x coordinate remains same. However, when I project this onto the time axis of the moving observer, these 2 events are no longer happening at the same position, and hence the difference in the time interval measured, because he is not measuring the time interval actually, he is measuring just the difference in coordinates. Moving on to length contraction. So is this also a result of measuring the same vector, that is this space-time vector, in 2 different bases? It is somewhat related to the procedure of measurement of length again. So the measurement of length is defined now as delta L should be measured along lines of simultaneity. So now what are lines of simultaneity? Lines of simultaneity are lines at which the time remains constant, that is parallel to x-axis. So for this line of simultaneity, so for this observer, what will the lines of simultaneity look like? It will look like something like this. That is, both the observers are not agreeing on their lines of simultaneity. To give you another intuitive idea to it, how is simultaneity the same for 2 observers, I will discuss this experiment. So what this experiment is about, so there are 2 observers in 2 trains, O and O dash, and there are A dash, B dash, A and B. So the train is moving at a speed v with respect to observer O. So a lightning strikes this point A dash and A and B dash and B when both the position of observer O dash and O coincide. So as soon as the lightning strikes, light signals from point A will go towards O, and light signals from point B will go towards O. So suppose this length is L, this length is L. So O will say that light signals from both A and B will reach to me at in a time of L by C. So he will say that the lightning strikes at A and B are simultaneous. However, as the observer O dash is moving to the right, as the signal from A dash comes out, to reach O dash has already moved by a distance Vt. So light is taking longer to reach O dash. It's covering a longer distance. So, and for B dash, O dash is moving towards B dash, and hence light would have to cover a shorter distance to reach O dash. Hence, observer O dash will say that the lightning strike at A dash is taking longer time has occurred later than lightning strike at B dash, because light signals from A dash are reaching later to him than light signals at B dash. Is it clear, guys? Any doubts about this? So two observers are not even agreeing on simultaneity of events, and we can graphically see that because their lines of simultaneity are no longer the same. This guy's lines of simultaneity are like this, and this guy's lines of simultaneity are this. So when measuring length, again, so we are measuring now two different vectors altogether. So suppose this is my train and this is the train back and train front. So for this guy, the lines of simultaneity would be in this direction, and he would measure the length of vector r to be the length of the train. However, in this frame of reference, the vector m represents the length of the train along his lines of simultaneity, because his lines of simultaneity would be parallel to Ex coordinate axis, and this is in this direction. So again, these two vectors will obviously not be equal. So upon applying Lorentz transformation, so it might look to you that this m vector is longer than the r vector. So this is again length expansion, but that is not the case. When we do the Lorentz transformation and all, the length of this m vector comes out to be the length of the r vector, and hence two observers will disagree on the length of the train and would say that the length of the object which is moving with respect to me is shorter than the length of the object which is in my hands. So if we have two rulers, and one ruler is in the hand of the stationary observer, other ruler is in the hand of an observer on a train, he would say that the length of the ruler on the train is less than the length of the ruler in my hand. This is again all the play of perception and frames of reference. There is nothing that the atomic distance between the scale has reduced or something. It is all relative. It is all due to change of coordinate transformations. And that would be it. And even if you did not understand anything, in the words of Einstein, relativity in the most simplest words is like if you are sitting with a nice girl for an hour, it might seem like a second. However, if you are sitting on a hot stove for 1 or 2 minutes, it might seem like centuries have passed. So that is relativity for you guys. Thanks for your time.
Okay, so till now we have seen what time dilation is, what length contraction is. I was actually expecting a question from the audience. Why did he draw lines like this? Like, why didn't anyone ask you? Anyone of you ask that question? Like, seems ridiculous, right? Why are you drawing inclined lines for some reason? Just because Lorentz transformation doesn't mean it's correct. What does exactly that line mean? So you're saying you have this Tx. This you agree? This is your frame. How is this guy's frame like this then? How did you draw this thing? Does this thing have any physical basis? Can anyone tell me why you draw lines like this? Or let me ask you a different question. Is this something which happens only in special relativity? For Galilean relativity, can you still draw something like this? So, okay, let's leave this. This is wrong. We don't know. How do you know this is correct? Let's start from the simple case. You have a car moving like this, and you say this slope is 1 by v. X is along the x axis and y t is along the time axis. So this slope is actually 1 by v and not v, as you would expect. So what are we exactly drawing when we say the time axis is like this? What does this mean? Anyone? Okay, first of all, what we are trying, I'll ask you my question precisely. You are still working in this coordinate system, and I want to know what this observer thinks two simultaneous events are. So let's say I have two events like this. Are they simultaneous events for this observer? No. Why? How do you know the observer doesn't draw his x-axis like this and say they are at the same time? But no one told you that for the observer the line of constant position is this. So tell me, so which is this line of constant position? So what would that look like? Like this? So even though this observer says that these events are happening at different positions, this observer will say they are happening in the same position. Agree or disagree? Because if you think about it, does the position of the observer change with respect to himself? No. Which means this must be a line of simul position for the observer. Is this the time axis or the x axis for the observer? Time axis. What will his x axis look like? Or ask more precisely, which two, let's say you have two events here, will this observer observe them to be simultaneous? No. What about these two? Are they simultaneous for him? I'll just erase this slightly and draw it better so you can see. This guy is moving like this. Are these two events simultaneous for him? No. Correct? Are these two events simultaneous for him? Are these two events simultaneous for him? No. Don't think about SR. Tell me, as a man who only knows Galilean relativity. Yes. Why do you say so? Okay, yes, you are correct, but the reason is because, as we said earlier, Galilean observers don't say that time is also getting changed. So whatever this observer observes to be simultaneous, every other observer will also observe them to be simultaneous. That was the principle of Galilean relativity. So his x-axis will also look like this, correct? So that the lines of simultaneity are all parallel like this. Very good. Now let's draw for this guy. Let's draw the lines for this guy. In SR, what does this mean? You have the same thing, some other observer moving like this. Now how will his lines look like? What is this? First of all, what is this line of simul position? What does his x-axis look like? So, if this is the ray of light, what are you saying is the relation? Anyone? So, the principle was all inertial frames are equal or equivalent, and the second was speed of light is the same in all local inertial frames. So, how would you fix the time x-axis now? Agree? What he is saying is the speed of light must be the same in both frames of reference, correct? Which means your dx for light, if this is the thing for light, these two must be equal to c. Isn't this what he is saying? Agree? So if the speed of light here is c, which means this slope is 1 by c. What we do is we write Ct instead, so that your speed of light your light ray becomes at a 45-degree angle. 1 unit of Ct in every 1 unit of time. So you write it as Ct and x, just for simplicity. So the point is, if so why does the equal angle? Where does the equal angle come from? Let's just complete this diagram with a parallelogram. Would you agree that this is correct? Will the light pass like this or like this? So this is your let's say you have somehow found your x axis. Would you agree that light passes through like this? So the point is this angle, let's say it's some theta, okay? Let's say this angle is some theta. For now we are not really interested in what this theta is. So what you want to show is that your dx by dt is the same c. This is what you want to show. So can we can go to the Lorentz transformation slide. So this is well known, right? This is established. There is no question that this is the Lorentz transformation. Okay, do you agree with this? This is the Lorentz transformation. We are not deriving it in this, but given that this is the Lorentz transformation, can you now see, okay, maybe deriving it this way is a bit difficult, and maybe this is a bit difficult. So for now we'll leave this. If you are interested, you can ask me later. We are already short on time. So point is, with these transform equations, you can fix the x to look something like this, and it turns out that these angles are equal. Yes, you can, and the derivation is a bit lengthy. We'll go, if you are interested, I can show you the derivation. I have it with me, but for the interest of time, we will not go into this. So point is, this x tilde represents events that this guy thinks are simultaneous. Agree? But you are not actually going into his frame. You are still staying in the original frame, and you are trying to figure out what simultaneous events look like for this observer. Correct? That is what this x tilde represents. Similarly, this t tilde represents events which this guy seems to be, thinks are at the same position. You are still in this guy's frame, you are still in the original observer's frame, but you are trying to figure out how the world looks like for this moving observer. That is what he drew there. That is what those basis vectors and all of that means this. So you are trying to figure out how the world is observed by this person while still remaining in this reference frame. Now here is the thing. Let's say you have two events which are simultaneous in this frame. As we already established, they need not be simultaneous in this frame. And similarly, if you have two events, simulposition need not be simulposition, simultaneous need not be simultaneous, because of the inclined nature of these two axes. So this guy says only these two events are simultaneous and these two events are simulposition, and this guy disagrees. The question becomes, can you universally define a time interval and a length between events? Can you? No. Who thinks here that you can? Who thinks that you can define a length and time interval between two events? Given that we just talked about time dilation and length contraction. No one. No one. Well, I am sorry to say, but you are all wrong. You can actually define a notion of length and time between two events. And the key is, see, we are restricted to defining delta t at constant x. First question, why didn't anyone ask why this is true? Like, you have never seen this, right? Have you ever thought about time intervals this way, that they must be at the same x position? No, why not? My question is, you have always talked about delta t. For length, you know that, okay, I must measure the endpoints at the same time. I shouldn't let the object move and then measure the length. Why did you never think of it that way for time? Time was independent. So it didn't matter that x was constant or not constant. That was a byproduct of Galilean relativity. It need not be that way. We know that to measure delta x, delta t, your x must be constant, and to measure your delta x, your t must be constant. This is obvious. This is its less obvious counterpart. Now, let's say you have two events. In this guy's frame, are they simultaneous? No. What about in this frame where this is your x axis? Are they simultaneous? So the point is, whatever this guy measures as delta x, that is the correct length, and whatever this guy measures as delta x is not the correct length. Why? Because he is not measuring them at the same time. He is measuring them at two different times. It's stupid. Why would you measure the length at two different times and say this is the length of the object? Obviously that won't remain the same. If your object is moving and you measure the length at two different times, you will obviously disagree about what the length of the object is. But this is the correct way to define distance. The events must be simultaneous. Similarly, you have two events here. What is the time interval between these two events? This guy, he doesn't see them at the same position. So how can you call whatever this guy measures as your delta t to be the time interval? This is the error. It's not that you misunderstood something in your life. You are trying to measure time when your events are not at the same position, and you are trying to measure your lengths when the events are not happening at the same time. That is why this disagreement comes from. If you restrict yourself to only measuring time when events are simulposition and length when they are simultaneous, there would be no confusion, because there is only one line in which they are simultaneous and there is only one line in which they are simulposition. So this is what we define as proper length. So proper length, you have two events, you first move to the frame where they are simultaneous and then you measure the length between them. Proper time, you have another two events, you first move to the frame where there are simulposition and then measure the time difference. Oh, I said the same thing. Simultaneous and measure the x distance. This fundamental principle, this confusion happened because we started thinking about only delta x and only delta t as length and time. That was not the case. We forgot that this restriction existed. Once we apply this restriction, there is no ambiguous notion of distance or notion of time between events. The takeaway here is your delta t is no longer the time interval between two events, and your delta x square plus delta y square plus delta z square is no longer the length distance between two events. Instead, you must first go to this new frame and then what you are saying is correct. Correct? Agree? So this is what you call proper time, the time observed by the observer for which the two events are happening at the same position, and this is what you call proper length, which is observed in the frame in which these events are simultaneous. Good. So we have already established that delta, this t and x, they are weird things. They are not actual time intervals or space intervals. Let's take this one step further. Have you guys heard of this thing, speed of light? So first, next question is speed of light always the same in every frame of reference? Who says yes, who says no? Who says the speed of light is the same in all reference frames as per SR? 1, 2, 3, 4, 5, 6. Okay, who says they are not the same in every reference frame? Why do you say that? But I told you na, speed of light is the same in all reference frames, or did I tell you that speed of light is the same? So I told you the foundational principle of SR is C only in inertial frames. Only in inertial frames. Not even that, it's actually even more restrictive than that, we will come to that later. But it turns out that from accelerating frames, you can measure the speed of light to be literally anything. For example, consider some, I am not going to go into exactly why this path is the path for constant acceleration. You can ask me later why I am drawing this specific curve. But the point is, it turns out that for accelerating observers, there exists a ray of light which appears to be at rest. The ray of light is at rest as seen by the accelerating observer. Its distance from the accelerating observer does not change at all. It is just frozen. Speed of light is 0. The speed of light is 0. Not only that, you can have even negative. So the light which is supposedly propagating in this direction, could you have it moving in the other direction? You can construct frames like that. You can construct frames in which the speed of light appears to be very close to infinity. There is no reason that the speed of light must be c. It can be 0, it can be c, it can be anything. But when you are in an inertial frame, the speed of light is c. That is all I am saying. So the thing is, we define what is the definition of speed? You say it's dx by dt, right? This is what you are saying. Here is the issue, x is not invariant, t is not invariant. Different observers say x is different, different observers say t is different. We never had this problem with inertial frames because it just so happens that Lorentz transformations make sure that this dx by dt is still c. It makes sure. But if you are in non-inertial frames, this x and t, this need not be c. This speed as measured by change in x by change in time is no longer c, because this is not representative of length and this is not actually representative of time. Remember, only a proper length and a proper time exists. These things are not lengths and times, as we've seen earlier. Just delta x is not length and just delta t is not time. So the takeaway I want you to get from this is, from now, whenever you see something in SR written x and time, don't immediately assume that this is space and time. It need not be the case. So now the question arises, what is length then? What is time? Let's say I like this reference frame and I want to know what is the length between these two events in this reference frame. I only know this delta x and I only know this delta time. How would I get the length between these two events as I would have seen if this were the observer? How do you go to this? I only know this frame. I don't know this frame, it's some random frame. Why should I talk about this frame? So now how do you get the interval between these two events? That is the question, right? Why would you want to go to this frame? This is some inconvenient frame. You know delta x and delta t. Can't you just work with this? This is actually the space-time interval. The space-time interval, if taken like this is actually the proper times, this is the proper time square into c square between these two events. And if you take the space-time interval, this is the negative of proper length square. Still working in these coordinates, the way you would get this proper time and this proper length is like this. Of course, you can replace it with the delta everywhere. If you are in this frame, it is still the same. You still use the same thing. It is c square delta t tilde square minus delta x tilde square minus. Does this make sense? Let's do a quick sanity check. To measure proper length, what is the condition? Delta t tilde must be 0. Is this length? I mean, this is minus L naught square. Is this length? So length is the same. We are not changing some fundamental aspect of what length means. It is still a spatial unit. Similarly, let's go if this is t tilde and this is x. Is this still proper time? Let's see, what is the thing? Delta x equal to delta y equal to delta z equal to 0. That is the equation of the t axis, right? Which means what? All of these terms become 0. You only have c square delta t square and you are saying that is c square proper time square. Does this make sense? So this is, what is this thing? This is your metric, correct? You are having 2 points. Your mistake was you thought the distance between them is delta x square plus delta y square plus delta z square, when in actuality it was given by this metric. It was actually minus c square delta t square plus delta x square plus delta y square plus delta z square. Because you had an incorrect notion of what length and these coordinates represent, you were fooled into thinking that, oh, delta x, delta y, delta z, that is length. No. That's not how it works in SR. This is the actual length. This is the actual length and this is the actual time interval with the negative and positive sign taken care of course. So your x is not length, okay, your time is not time. What else? We have established that speed of light is not c. Anything else? So the key takeaway here is, whenever you are talking about something in SR, it only makes sense to think of these coordinates when you have the metric. These coordinates alone need not have any well defined meaning. For example, instead of t and x, I could have just as easily taken x minus ct and x plus ct. Why is this not a coordinate system? It is also a labeling of coordinates, except instead of t and x, I have written x minus ct, x plus ct. Is this a coordinate system? First of all, this is a coordinate system, correct? What is inherently wrong about doing SR like this? Nothing, except this is no longer this is not a length, this is not a time either. This is also not a length, this is also not a time. But these are the same. Any calculation that you do in this is the same calculation that you will do in this. The answers will be the same. So SR's fundamental notion is that this t and this x are no longer separate quantities, with t having this very special space and you should not mix it with x. You should not, if someone in kinematics wrote this, they would get 0 marks. Because you are saying now space and time are the same. That is not true in Galilean relativity, but it is true in SR. So the key takeaway is, what you call your length and what you call your time, if you define them as delta x and delta t, when you change reference frames, your results will become incorrect. And it will become simply false in some other reference frames. None of these coordinates are especially unique. If you change your metric to this coordinate system and derive your results in this coordinate system, that is equally valid as deriving it in this coordinate system. So the conclusion is, metric is the king. Your x, t, c, you can take them to be anything. Instead of x, you could have used x square. X square is also a valid quantity. Why is x square not a valid quantity? You can do your calculations with the t square, x square axis. Just use the correct metric and you will still get the correct answers. So x is not length, t is not time, speed of light is not speed of light if you define it as this way, and only the metric matters. That is all I want you to take away from this session. So there is this very nice line which I like to quote. In special relativity, you can't trust your eyes. What you call length and time, you can't trust them. You can only trust the metric. Using this, now I'll just finish it with one last point. How would you find the proper length and proper time between events along this path? Let's say you have some random path. What would you do? But how do you know the metric still works here? You divided it. It is still not a straight line. It is still not a straight line. How do you know that your SR will work the same way? Let's say I divide it even further. Even now it's not a straight line. What do you do? So here is the key. Instead of taking any finite length, you say that in the limit of your length going to 0, in the limit of this interval going to 0, you can say that this curve and this line are the same thing. Similarly, this curve and this line are the same thing at this point, and this curve and this line are the same thing at this point. So what you do is you go to these are inertial frames. You can do calculations in the vicinity of this point, assuming that this is your actual frame and you are not actually moving on this curve. That is what you do. So instead of talking about accelerating frames as a separate thing, what you do is you convert the accelerating frame into many inertial frames and solve them as the union of all of those inertial frames. So this is how you deal with acceleration. Now I will let you off with this. Thank you for attending this session. If you have any questions, you can stick around. We'll be here to answer your questions.